Hey there, AP Chem Scholars. We're going to take a little dive here into Unit 5. Okay, it's all about reaction kinetics, and Section 1 has to do with the idea of rates of reaction. But there's a whole lot of background that I want to kind of review, assuming you heard this before in your previous chemistry experience. When we talk about reaction kinetics, we're filling in the gap between reactants and products, okay? Up until now, we've said, all right, we start with reactants, we end with products, but we never said how we go from reactants to products. So that's what kinetics is all about. It's about how we get from those reactants to the products, what's going on in between A and B, okay? So there's a lot of things that go into this process, but the most important underlying thought is the idea of collision theory. Okay, so collision theory is the basic idea that in order for a reaction to happen, the reactants need to collide with sufficient energy and also sufficient geometry in order to break the bonds and start the process of making new bonds. This would even be true for a decomposition reaction because we need two of the same substance to break apart somehow. And so obviously it's not just going to fall apart necessarily. It's going to take a certain amount of one molecule of, let's say, aluminum carbonate colliding with another molecule of aluminum carbonate, causing carbon dioxide to start popping off, and so on and so forth. So everything comes down to that. Okay, now we're not going to focus too much on the geometry thing, but understand that they have to collide at the right way in order for the bonds to break. Okay, so if I'm talking about hydrogens and oxygens colliding, and I want to break the bond between the hydrogens, then if the hydrogens and oxygens collide like this, it might not work. But if they come like this, now the oxygens are hitting between the two hydrogens, are coming right towards that bond. Now it's got a better chance. Why is that important? Because there's going to be millions of collisions and maybe only a few of them are favorable. Okay, so when we talk about the idea here, there may be a lot of collisions that just don't work. And one of the goals would be then, how do we help that along? How do we make it work better? So in that mode, let's talk about a few reactions. Okay, the first one is the combustion of propane. Then we have the synthesis of hydrogen chloride gas. And then we have the synthesis of iron 3 iodide. Okay, so let's think about these in terms of what you think is the fastest, which you think is the slowest. All right. The combustion reaction is all gases. Okay, we know that gases are moving better, so there's a better chance of them colliding and colliding with sufficient energy. So that means this reaction is pretty good. It's pretty favorable. On the downside, though, we're talking about remember, in the collision model, we're talking about 6 molecules colliding for this to happen. Now, 6 of them colliding at the same time is almost an impossibility. And 6 of them colliding with the right geometry at the same time, that really is virtually impossible. Okay, so this is going to happen in a series of collisions. So propane collides with an oxygen, and then whatever is formed from that collides with another oxygen, and so on and so forth. So this has got a whole bunch of things that's going to go on to get from here to here. By contrast, if we look at the hydrogen chlorine, okay, all I need are those hydrogens and chlorines. I have one of each to collide with the right geometry. This one should be real easy by comparison. Okay, this is definitely the fastest reaction because, again, it's also gases that are combining. Okay, so getting this reaction to happen should take very little input. On the other hand, this one is decidedly the slowest. Even though it has less molecules on the reactant side than the propane, we're dealing with solids. Okay, and so the odds are, even if we put the two solids on top of each other, that either no reaction would happen or very little reaction would happen without some inputted energy or something else. I'll save that something else for a little while. Okay, so definitely the slowest reaction. I mentioned that the propane reaction would happen in multiple steps, okay? That is what a reaction mechanism is, okay? We have to recognize that we don't automatically go from reactants to products in most cases anyway, that there are steps that happen along the way. Now, we don't necessarily have to know how to write out a mechanism. We have to recognize that there is a mechanism and that there are a series of steps, and some steps are going to happen fast, some steps are going to happen slow. And so when we recognize this, then we can recognize a way of actually trying to make a reaction happen faster. Okay, so reaction mechanism is a set of possible steps for each collision in a reaction. So here is a mechanism for that reaction we were just looking at. Okay, one of the nitrogen dioxides collides with the fluorine molecule and splits that fluorine molecule. Part of it sticks to the NO2 and the other piece floats off. Well, fluorine does not like to be monatomic, so that fluorine atom now collides with a second. So this fluorine atom is this fluorine atom colliding with a second NO2 to make a second NO2F. Okay, so notice overall, if I add these two steps together, I have two NO2s, I have two NO2Fs, I have an F2, and then these would subtract out because I'd have one on the right side, one on the left side. Okay, just like we talked about with our spectator ions, not that I'm calling this a spectator ion, but just showing you that we could factor that out when we add up the reactions. So the overall reaction is still this, but the two steps make sense. Okay, so what about that fluorine then? Sometimes when we look at the overall reaction, we know that there are other things being formed in between that just aren't part of the overall reaction, okay? And those are called intermediates, okay? So going back to the propane one, there would be, I'm sure, many different intermediates formed as the propane starts colliding with one oxygen and then another and so on and so forth, okay? All right. We often try and identify the rate determining step in a reaction. Okay? Rate determining step is just the slowest step. Okay? Why is it considered rate determining? Because it's having the biggest impact on the rate. All right. If you're trying to speed up a relay team, that slowest person is the one that's got to really step it up for everyone else. Okay? When we look at a reaction, the one that's taking the most time, even if it's just 1 extra second, it's still having the biggest impact on the reaction. So that's where we would focus. All right, we're going to talk about that a lot more when we get into the next two sections. Going back to this, should we be able to identify the rate determining step? Yes, we should be able to. Okay, looking here, okay, when I bring these two together, I have to break a bond between fluorine and fluorine. But when I bring these two together, I don't have to break a bond. Okay? Yes, I have to make a bond, but I had to make a bond here and here. Okay? So the bond breaking is what's going to make this a slower step and this a faster step. Okay, so now the question is, let's say we've identified a step and we want to now talk about how to speed it up. Okay, well, there are 5 ways of speeding up a reaction. I'm going to talk about it from this example here of taking some aluminum foil and throwing it in some hydrochloric acid. So what are some ways we can speed this up? I can use more of a reactant, okay? Just keep pouring in HCl, okay? That's gonna create more collisions between HCl and aluminum, which means that there's gonna be more chances of the reaction occurring. Instead of balling up the aluminum foil, I could shred it, make it a powder, and then pour the acid on it. That reaction would happen almost instantaneously at that point. Kind of tied into the same thing as the first one, instead of just saying we're using more of a reactant, what if we just increase the concentration? So instead of using 0.1 molar hydrochloric acid, use 10 molar. Okay, now you're talking about something that is 100 times more concentrated. So now you're going to have 100 times the number of collisions happening, it's going to be much more favorable. Next, we could add energy, and that's probably the first thing that most of you thought about. Energy does not have to mean heat, though, so please understand we're talking about any type of energy. Sometimes stirring a reaction is enough. We're giving it mechanical energy. Sometimes we need electrical energy, a little spark to get things going, if you will. Okay. Sometimes light or light energy or electromagnetic radiation will get a reaction going. So any form of energy is going to give us more energy of collision, right? And that's what we need to make sure that we have better collisions. And then we have the catalyst, okay? A catalyst is a chemical that speeds up a reaction without being consumed in the process. So it's something that goes in like a reactant, but it's produced later on, so we get it back. So if I start with 20 grams of it, I end with 20 grams of it, okay? It is not consumed in the process, okay? I'm showing an example of something I use all the time. This is it's not a saline solution. It's actually a hydrogen peroxide solution for cleaning contacts. Putting hydrogen peroxide in your eye is definitely not a good idea. But what they do is they put a palladium contact at the bottom that helps speed up the decomposition of hydrogen peroxide. So instead of it taking days or weeks to decompose, it takes about 4 or 5 hours for it to decompose. And when it decomposes, it breaks down into water and oxygen, neither which is bad to have in your eye. So you get the cleaning power of peroxide, but the catalysis allows it to break down at a good enough rate that by the morning you can put it in your eye and not really want to scream. All right, so now that all that background is out of the way, let's talk about what is a rate. Okay, a rate is defined as a change in amount over time. You've talked about rates in physics class, I'm sure, maybe even in math classes, okay? It's the same idea, except for us, an amount is going to be something like a change in amount of moles, a change in molars, a change in atmospheres, a change in liters, okay? Over time, of course. We're going to talk about rate of a reaction. Talking about a rate of reaction is a generic term, though, because like to say that the rate of reaction is, 3 molars per second. 3 molars of what? Of everything? Because keep in mind, some things are being produced, some things are being consumed, so we can't talk about it that way. So the idea of a rate of reaction is a very generic term, assuming that we're talking about a product that has a coefficient of 1 in the balanced equation. Yes, I know there may not be a product that has a coefficient of 1, but that doesn't matter. It's still defined that way. And the point then is that the coefficients we're going to say that the amounts are proportional to those coefficients. I'm sorry, the rates are proportional, okay? So that means stoichiometry is going to play into this, okay? Like I was saying a moment ago, some chemicals are consumed over time, some are produced. So when we look at the rate of a reactant, okay, we're going to see it decreasing over time. It's going to have a negative rate, okay? Physics people, calculus people, okay, rates are related to slopes or derivatives, if you will, okay? No, we're not getting into that, okay? But obviously this has a negative slope, it has a negative rate. This has a positive slope, it has a positive rate, okay? So products increase over time, reactants decrease over time. And yes, they are stoichiometric, okay? So the bigger the coefficient, the bigger the rate. Everything is proportional, okay? Don't worry about this as something you need to memorize. Just understand it is stoichiometric, okay? So if we're talking about something like, for example, let's say this was 3 hydrogens and a nitrogen making 2 ammonias, okay? The fact that there's 3 hydrogens to 1 nitrogen means that hydrogen's rate is going to be 3 times the rate of nitrogen, okay? Ammonia's rate is going to be 2 times the rate of nitrogen. Okay, so it is proportional to those coefficients. Okay, and we will talk about rate stoichiometry. Okay, so for example, we have a reaction here of hydrogen plus oxygen and nitrogen making hydrogen nitrate. We're told that the rate of reaction is 1.5 atmospheres per hour. what is the rate of consumption of oxygen? Well, remember that the rate of reaction is assumed to be something that has a coefficient of 1. So we'd say that the oxygen is 3 to 1 with that substance. So it's 3 times the rate of reaction, but it's negative because it's a reactant. So we would say it is decreasing at a rate of 4.5 atmospheres per hour, or have a rate of negative 4.5 atmospheres per hour. Okay. Likewise, we're talking about the hydrogen, okay, since a coefficient of 1, it would be exactly equal to, and bad me, I forgot to put the negative in here, so that should be, oh wait, no, it says hydrogen nitrate. Sorry, I didn't read it right. Aha, I did it right though. Okay, so hydrogen nitrate has a coefficient of 2. Okay, so I could compare it to the oxygen and say it is 2/3 of oxygen. What's 2/3 of 4.5? 3. Let me get rid of that one there. Okay, or I could say, again, comparing it to the rate of reaction, since it's 2 to 1, because again, the rate of reaction is always assumed to have a coefficient of 1, 2 times 1.5 is also 3. So you see, it's really basic stoichiometry. You're not going to be doing conversions or whatever. It's all about just that ratio. All right, that leads us into the idea of ice tables. Okay, I'm going to talk about that real briefly before I wrap up this video. Okay, when we were doing limiting and excess, we had to talk sometimes about figuring out how much of the excess reactant was left over. We were doing this idea of ice tables way back then. In an ice table, the I stands for initial, C stands for change, E stands for N. Keep in mind, as we're doing this rate stuff, we're talking about change over time. So this change is related to the rate of the reaction, okay? So we're going to incorporate that along the way here. So for example, if we begin a reaction with 10 atmospheres of propane and 10 atmospheres of oxygen, we find that the carbon dioxide is made at a rate of 0.04 atmospheres per minute. If the rate stays reasonably constant for 1 hour, what is the partial pressure of each gas? Okay, so let's talk about what we have in there. Okay, we know initially that we have 10 atmospheres of propane, 10 atmospheres of oxygen, and we could reasonably assume we don't have carbon dioxide or water yet because they're products. We don't start with products. Then we could talk about the change. We know that carbon dioxide is being made at 0.04 atmosphere per minute for 60 minutes. So if I multiply 0.04 atmosphere per minute times 60 minutes, I get 2.4 atmospheres. The change line is the stoichiometry line, okay? That's what we've been doing stoichiometry for all along. Everything that we have done, we've talked about how much of something we've used, how much of something has been made. We're talking about how much of it went down or how much of it went up. Okay, when we talk about how much was left over, well, that was excess, and that's where we get to the E in a moment. Okay, so let's talk about the stoichiometry here. If I know I have 2.4 atmospheres of carbon dioxide being made, now I'd start doing some proportion. So let's talk about the propane. The ratio between propane and carbon dioxide is 1 to 3. A third of 2.4 is 0.8. But again, I have to make it a negative, okay? You notice when I do the stoichiometry here, reactants coefficients I put in as negatives, products I put in as positive. That handles it. But as long as you remember that the reactants have to have a negative rate, that's really all that matters. Okay? What's the ratio between oxygen and carbon dioxide? 5/3. What's 5/3 of 2.4? Well, it's -4. Okay? And then what's the ratio between water vapor and carbon dioxide? That's 4/3. 4/3 of 2.4 is 3.2. So there's my change line all filled out. That's how much this is going down. That's how much this is going down. That's how much this is going up. That's how much this is going up. So now at the end, we can put it together and say, all right, at the end of an hour, there's going to be 10 minus 0.8 or 9.2 atmospheres left of the propane. There's going to be 10 minus 4 or 6 atmospheres of the oxygen. There's going to be 0 plus 2.4 or 2.4 atmospheres of carbon dioxide present. 0 plus 3.2 or 3.2 atmospheres of water vapor present. Okay? Now you could even more easily see that oxygen is going to be the limiting reactant because we're going, even though we started with equal amounts, I'm now significantly less, I have significantly less oxygen at this point, and so on. So we're going to be using these ice tables a bit as we do stoichiometry. All right, I'm rambling, so I'm going to stop there. Go try that AP practice.